Well, thank you, Tracy. So I think this is a good follow-up to Bob's. So I'll start by just pointing out, I think most of our discussions so far during the meeting have been about this question of, or addressing this question of ocean surface exchange and the fact that that is extremely relevant and crucial to understanding the surface composition and the relationship of the surface composition to that of the ocean. But there is a second element to this problem as well, which is the interaction of the surface and the surface composition with the atmosphere. So you have sputtering of radiolysis products from the surface. That removes molecules from the surface. It alters the surface composition. That itself feeds back into the radiation chemistry, which then alters the exospheric composition. So there is this equally intimate relationship between the surface and the atmosphere. And that is one problem. The composition of the material ejected from a surface material into the atmosphere that has not been nearly sufficiently explored through laboratory experiments. So I'm going to discuss that a little bit here. So just briefly, this is just a small sample of some of the experiments that have been done to measure the evolution of the composition of mixed ices. So here are some examples. On the upper left is a mixture of water and methane irradiated by MeV protons. We have a mixture of water and CO2 and another water and methane mixture with 100 kilovolt protons. And you can see the evolution of the optical reflection spectra of the surface indicating different radiation products with different atomic combinations of carbon, hydrogen, and oxygen being formed. But something I think that's missing here and that you really need to interpret the atmospheric composition at Europa and its relationship to that of the surface is to measure during such an experiment the amount and composition of radiation products that are ejected from these ices. Unfortunately, there is not nearly as much work's been done on that problem, but as Bob's just talked about here, in one extreme case, you have the situation where you have a heavy energetic ion, and those ions have very high sputtering yields, as Bob has just pointed out, and due to the formation of a thermal spike around the ion track, so you get these huge numbers of molecules ejected to the from the surface material, and those rates can far exceed the rate of radiolytic processing of the material. So you can, in principle, have a significant proportion of intact large molecules ejected from the surface in this regime. Now, one question that raises is that at Europa, you have significant gravity, so anything that you eject from the surface can fall back to the surface, can stick to the surface, and so presumably would have very many opportunities to get dissociated. So the actual amount of these large molecules, or the proportion rather of these large molecules as a proportion of the total amount of material sputtered, is a big question, and I think that will have a dependence on the number of opportunities or the number of times that these things fall back to the surface, stick to the surface, and have a chance to be dissociated on the surface. Presumably, the material that you eject from the surface is some combination of these endogenic large molecules, if they are present, and their dissociation products. So you also have to address this problem, you have to address what happens at the other, I'll call it the other extreme of energy, of ions at much lower energies, where the rates of sputtering and the rates of chemical radiolysis of the surface are comparable. And so these are just a few of, I mean, there's only a handful of such measurements on the composition of the material ejected. I'm going to step away from the microphone here.
Need to be on.
Can they hear me?
No, you have to have it.
Okay. All right.
Not the.
Yeah. If you could set that up for me. And so these are just a few such experiments. You have on the upper right, upper left there, pure water ice, and that shows the evolution of molecular oxygen emission from the ice as a function of radiation dose with protons. On the lower left is pure carbon dioxide ice from Rout et al. And you can see in both of those experiments, you have this buildup of O2 as a function of dose, showing that there's some analogous chemical processing of both the CO2 and the H2O ice, in the sense that both ices accumulate trapped molecular oxygen and oxidants, radiolytic oxidants, in the solid. They become oxygenated. And so that shows up in this dose dependence of the O2. But then you go to something like, so take the CO2 and replace the oxygens with hydrogen. So this is an experiment. This is 1987, and this is irradiation of solid methane. And these guys were measuring same kind of thing, the ejected flux of, so this is mass 2, so that's molecular hydrogen as a function of time or irradiation dose. This is methane. It starts high and then drops, and then you have these heavier hydrocarbons that are formed on the surface. And they actually measured many hydrocarbons. This is just a plot of one of them. If you look at their paper, there's a mass spectrum that shows that many higher order hydrocarbons are formed from the methane, and they are ejected from the solid. So you have this process of I'll call it carbonization of the ice, or rather dehydrogenization, where rather than oxygenating the material, you're carbonizing the material. And so the direction in which that I mean, here you have an ice that also contains carbon. So why was that not carbonized, or rather than being oxygenated? And, it's a dependence of, it depends on not only the chemical reaction rates in this radiolysis process, but the volatility of the products that you produce and their ability to be sputtered. And both of those things interact together at the surface of the material to determine whether, or rather which direction it goes. Does it become oxygenated or hydrogenated? Now you can put species, you can add nitrogen or something or other elements into the mix, and some other version of this process would presumably happen. So, and these are the other hydrocarbons, and you can see that you have this evolution with the radiation dose during the experiment. One thing I'd like to point out is that all of these over time, so the yields are high, and then they drop over time during the experiment. And so what's happening here is that you're more or less converting the methane into some version of graphitic material, and the sputtering yield of that material is very low. So all of the yields, the higher order hydrocarbons, even the molecular hydrogen and the methane, as you're destroying the methane, drop because the total sputtering, the total sputtered flux from the material is dropping as you are converting volatile methane into non-volatile graphite. So you can see that everything is dropping. And that raises the question, so if you just think about this space of water ice mixed with, you can think about CO2 on one end, and then becoming progressively more mixed with organic molecules. How much of these organic molecules do you need to mix in before you start to go in this direction and form graphitic-like surfaces, a graphitic-like material on the surface? And so how might this type of process work? Well, this is just a crude diagram. I'm representing a smooth ice here. Of course, on Europa it will be granular. But this just gives a sense of how this type of process might work. You have fresh material below the range of the energetic particles. the surface is being sputtered. And so rather than show the sputtered surface receding down into the ice, I'm moving into the reference frame of the surface, following the surface as it becomes sputtered. So you can think of it as, in a sense, the fresh material from below is coming up to the surface and is then being ejected. I just find that that's an easier way to think about how this type of process works. So you have fresh material from below. There's this thick region. I mean, the energetic electrons can go centimeters into the ice. And so the material is being radiolytically processed all throughout this thickness. But then there's a very thin layer at the surface, presumably, I mean, could be angstroms thick, or the region near the surface of the ice, or rather the surface of the regolith grains, where molecules can be sputtered or volatile radiolysis products can desorb. And so if you want to think about a simplified model of this, you can think about a layer here where one set of chemistry is happening, and then another type of chemistry is happening at the surface, which is influenced by this loss of material. And you can see also that different parts of the optical spectrum will sample different ranges in this material. That's better. All right, so at the same time, you have Europa's gravity. So material that's being sputtered can fall back to the surface, return to the surface, and that will compete with this loss of molecules from the surface. And so all of those effects compete and conspire to determine the ultimate surface and ejected composition. In addition to that, you can have particles bombarding the surface and re-exposing fresh material from below this very thin layer. That will do two things. First of all, it will eject the material that's there and contribute to the ejected flux, and then it will re-expose new material, which will then readjust its surface composition to compensate for the fact that the fresh material has been exposed. And so this is I just wrote down the form of a rate equation, and you can think about that you have n number of rate equations for all of the different major reaction pathways that may happen in this region and happen in this region. And so a simple model of this type of process, you might have, I'm calling it a source of product A, product B, product C, D, and so on, which is this material from below feeding up into the surface layer, and then the loss of these materials from the surface, which enter into these rate equations and determine the reaction chemistry. So you want to understand this process, but then also you want to know what these loss rates are, because that's your ejection rate into the atmosphere. That's what feeds the atmosphere and helps to determine the atmospheric composition. And then you have an analogous set of rate equations for this lower layer here. You have the source of fresh material into the layer from below, and the loss of material from this layer into the surface lagged layer. And so you can think about some general constraints that this type of problem would need to satisfy. One is that when things are allowed to evolve to steady state, the atomic composition or stoichiometry of the fresh material below the process layer should be preserved in the ejected composition in that steady state. So the number or the relative numbers of carbons, oxygens, hydrogens, and so on in the underlying material should be reflected in the composition that's sputtered. That's not to say that the molecular composition will be the same. You know, the atoms are being rearranged in this process, but the elemental composition should be tied to the material below. The surface will get concentrated in low volatility radiation products that will they'll have a high sublimation energy, so they will tend to resist sputtering. We saw that in the previous plot with the sputtering of methane, that the sputtering yields start very high but then drop drastically. Now, that again depends on your ability to form those non-volatile products. If there's no chemical pathway that leads to graphite, as in the case of water ice or CO2 ice, then that's just not a pathway that you have. So the sputtering of those materials may remain high. But if there are chemical pathways that form these refractory materials, presumably the surface material would acquire this resistance to sputtering. And then finally, the volatile products. So even if this graphitic surface were to form, if you just look at the composition of what is sputtered, the little amount of material that is sputtered, you should find that the most volatile radiation products are the most heavily represented in that ejected material. So if you see what I'm saying, so the total amount of material will be low. So this goes down. The surface material has evolved to resist sputtering, but if you look at the composition of what is coming off, the volatiles should dominate that composition. And so this just more or less shows schematically the type of thing I've been talking about with the dehydrogenation of the ice. And this is one lab experiment that we did with pure methane, or rather, this is methane. I believe this is methane mixed with water ice. And these are microscope images of the residue that's left over after the ice has been thermally desorbed. We are in the process, as I'll talk about in a minute, of measuring the composition of what sputtered off of that material. So that's what we need to know for the Europa problem of Europa's atmosphere. You can see it's very interesting. It forms this kind of cracked, patchy material, and we're working to understand that better. So to that end, we've been developing, this has been now a 2-year effort at SWRI, a laboratory setup to measure, the focus of this research program is volatiles throughout the solar system, icy satellites, and the physics of ices and volatiles on those objects, and also on the moon as well. It's another thing that we're pursuing. But this is our Europa ice simulation chamber that we're just now bringing under operation, and we're starting to get to work on some of these experiments. And that's just a schematic of the setup. We have an infrared spectrometer, visible and UV spectrometers, a mass spectrometer to measure the composition of the sputtered flux, an ion gun. We're installing an electron gun to do the experiment with electrons, and a quartz crystal microbalance to very precisely measure the total amount of material sputtered as a function of dose, irradiation dose during the experiments. So we should be able to characterize these processes quite nicely. This is just a summary of some of the preliminary experiments we're going to try to do. Water and CO2, mixtures of water and methane, and we're building a Knudsen cell to mix water with amino acids and see what happens under those conditions. So we'll see how those experiments go. And this is our website if you guys are interested. We have the facility, we have the setup here now to do these measurements, so we can use all the support we can get to continue this work. So with that, I'll take questions.
Hey Ben, can you go back to the slide that has the methane and your oxygen paper and the carbon dioxide one real quickly? I guess Foti et al. 1987. I guess I was a little confused. You said higher order hydrocarbons, but then you keep saying graphite, and they're really different. So, because I saw on your slide, you got ethane and you're getting hydrocarbons, but that's not graphite.
So what happens in this process is that you start with the methane. Methane becomes dissociated and you form H2, which rapidly leaves. So now you have a deficit of hydrogen, and those products combine to form higher order hydrocarbons.
Right.
And you continue that process and form higher and higher order hydrocarbons. You can see that you're building up higher amounts of carbon as the process continues over time.
Right, but graphite's a really different crystal structure than just these molecular hydrocarbons.
Well, you won't get pure graphite because there is a finite sputtering rate. So there is fresh methane from below that's resupplying the hydrogen, but the rate is slow enough that you get some highly enriched carbon, most likely with a small amount of hydrogen remaining in it in steady state. What crystalline form that takes, I don't know.
Well, I mean, if it's molecular versus, graphite is we can talk more later.
Possibly amorphous carbon.
So exactly.
Yeah.
Okay, that's exactly what I needed to know. Yeah, okay, thank you. Thanks.
So it's essentially between pHs and
Yeah, okay, I was thinking more pH. Thank you.
Other questions?
So where's this facility?
This is at Southwest Research Institute, San Antonio.
Okay, not Boulder.
Not Boulder, no, San Antonio.
If you had methane deposited in a place on Europa where it would be sputtered but also degraded into other stuff, what are the prospects for cold trapping materials elsewhere on Europa? Are there any places where they might be deposited and less likely to be destroyed and sputtered away?
Well, to cold trap methane or other?
Methane in particular, but others as well.
Well, methane, you need a very low temperature to cold trap it. And, so you can think about the fact that the tilt of Europa to the sun is extremely low, so there's not much of a season there. But to the extent that there are shadowed areas at the poles, it's probably not much of the surface area, but I guess there's a remote possibility that there could be some shadowed areas at the poles that would get that cold. That's not going to be much. But if such spots existed, you could cold trap methane at those temperatures and then radiolytically process it. But if you have organics or stickier species coming from a plume, for example, the areas on which those can be stuck to the surface and cold trapped are much more extensive.
Well, and I guess the second part of that question was their likelihood of surviving in Europa's radiation environment. If, for example, at the poles, is the radiation sufficiently lower at the poles that you would expect them to live for appreciably long periods of time?
you also have photons. Sorry.
You also have photons. So if it's a transient event like that, let's say a plume, and you have a plume and then it stops, and so there's some fresh plume material stuck to the surface, you're processing the material, radiolytically processing it, you're sputtering it. Now, again, some of that can be sputtered by the high energy ions. It's in fact more likely, perhaps, that you would see large intact molecules sputtered by high energy ions in that case, because you've just refreshed the surface with a fresh composition. As to how long that would take, I've done back of the envelope estimates that suggest maybe 30 days before it's fully processed, but that's just a very crude estimate and something we need to further examine.